space of n tuples. Let F be a field if A1, A2, A3 and so on An belongs to F, then in bracket A1, A2 and so on An is called an ordered n tuples. Point, the set of all n tuples is denoted by Vn or F power n. Let alpha equal to a1, a2 and so on an, beta equal to b1, b2 and so on bn be two n tuples, then alpha and beta are said to be equal if a1 equal to b1, a2 equal to b2 and so on an equal to bn. It is denoted by alpha equal to beta, and alpha plus beta sum of two n tuples equal to a1 plus b1 first term plus first term and second term plus second term and so on an plus bn. And if alpha is an n tuple and C belongs to F, then multiplication of alpha by C is defined as C alpha equal to CA1, CA2 and so on CA. Properties of vector spaces. If V of F is a vector space over the field F, then these 8 are properties of vector spaces. Proof. First property, A into 0 equal to 0. 0 belongs to V, A belongs to F. Consider A into 0 equal to 0 can be written as A into 0 plus 0, that is A0 plus A0. Next, A0 can be written as 0 plus A0, that is equal to A0 plus A0. That implies 0 equal to 0, A0 from the cancellation, right cancellation law, A0 equal to 0. Next, second property, 0 belongs to F, alpha belongs to V. 0 into alpha equal to 0 can be written as 0 plus 0 into alpha, 0 alpha plus 0 alpha. 0 plus 0 alpha equal to 0 alpha plus 0 alpha. By the right cancellation law, 0 equal to 0 into alpha. This is the second property. Next, third property, consider, third property is A into minus alpha equal to minus of A alpha. So consider A into alpha plus of minus alpha, that is equal to A into alpha plus minus alpha is 0. A into 0 equal to 0 by the first property. So A alpha plus A into minus alpha equal to 0. Here A into minus alpha is the additive inverse of A alpha. But inverse of A plus B equal to B plus A equal to E. Here B is the inverse of A. That is B equal to minus A. So same as here A alpha inverse is minus A alpha. So here A into minus alpha is additive inverse, but A alpha inverse is minus A alpha. So therefore A into minus alpha equal to minus A alpha. Fourth property, minus A into alpha equal to minus A alpha. By the third property, A into minus alpha equal to minus A alpha. We take minus alpha this side, that is plus A alpha equal to A into minus alpha. A into minus alpha equal to minus A alpha, that is equal to A plus of minus A into alpha. So A alpha plus minus A into alpha equal to 0, that is equal to 0 into alpha. Therefore minus A into alpha equal to minus A alpha. Next, fifth property, A alpha equal to 0. Suppose we consider A alpha equal to 0 and alpha not equal to 0. We can prove A equal to 0. Fifth property is, if A alpha equal to 0, either alpha equal to 0 or A equal to 0. We consider alpha not equal to 0, then we can prove A equal to 0. If A is not equal to 0 belongs to F, F is a field, satisfies inverse property, so A inverse belongs to F exists. Multiply A inverse on both sides, we get this equation. Next, A inverse into A equal to identity, so alpha, and A inverse into 0 equal to 0. So alpha equal to 0, which is the contradiction. Why? Because we take A not equal to 0, we get the contradiction. So therefore A equal to 0. Next, A into alpha minus beta equal to A into alpha plus of minus beta. That is equal to A alpha plus A into minus beta. That is equal to A alpha, A into minus beta equal to minus A alpha from the fourth property. So A alpha minus A beta. Next, seventh property, Suppose A alpha equal to B alpha, that implies A alpha minus B alpha equal to 0. Seventh property, suppose A alpha equal to B alpha, that implies A alpha minus B alpha equal to 0. Alpha is common, A minus B into alpha equal to 0. From the fifth property, if A alpha equal to 0, then either alpha equal to 0 or A equal to 0. Here, if alpha is not equal to 0 means definitely A minus B equal to 0. That implies A equal to B. So, if A alpha equal to B alpha, that implies A equal to B. If alpha not equal to 0. A alpha equal to A beta, that implies A alpha minus A beta. A is common, alpha minus beta equal to 0. If, here is also if A not equal to 0 means alpha minus beta equal to 0. Then alpha equal to beta. These all are properties of vector space. Theorem. Let V of f be a vector space. First one, if A comma B belongs to F and alpha belongs to V, where A not equal to 0 vector, then A alpha equal to B alpha, that implies A equal to B. Next, second one, if A belongs to F, where A is not equal to 0 and alpha comma beta belongs to V, then A alpha equal to A beta, that implies alpha equal to beta. Next, proof. V of f with a vector space and A comma B belongs to F and alpha belongs to V, where alpha not equal to 0 vector. Consider A alpha equal to B alpha, then we need to show that A equal to B. First one, if A alpha equal to B alpha, then we take B alpha and equal this side, so A alpha plus minus B alpha equal to 0. Alpha common, A minus B equal to 0, then A minus B equal to 0 as alpha not equal to 0. Then if alpha not equal to 0, A minus B equal to 0. So that's why A equal to B. Next, case 2. If A alpha equal to A beta, next A alpha minus A beta equal to 0 vector, common A, so alpha minus beta equal to 0 vector. Given from this statement A is not equal to 0, so next alpha minus beta equal to 0. Therefore, alpha equal to beta. Let V be the set of all pairs of real numbers and F be the field of real numbers with defined x1 y1 plus x2 y2 equal to. Second answer, 3y1 plus 3y2 comma minus x1 minus x2, and C of x1 y1 equal to 3c y1 comma minus c x1. Now we want to check V of f is the vector space or not. So first property is closure property. Let alpha equal to x1 y1, beta equal to x2 y2 for all alpha comma beta belongs to V. So alpha plus beta equal to x1 y1 plus x2 y2, that is equal to 3y1 plus 3y2 comma minus x1 minus x2. So this is belongs to V. So V is closed. Next, associative property. For all alpha, beta, gamma belongs to V, where alpha is x1, y1, beta, x2, y2, gamma, x3, y3. So LHS alpha plus beta plus gamma equal to x1, comma y1 plus x2, y2 plus x3, y3. First, in this term, we apply what can defined in problem. So 3y2 plus 3y, second terms 3y2 plus 3y3 comma minus x2 minus x3. Again x1 y1 plus x2 y2 form. Next, so 3y1 plus 3 into minus x2 minus x3 comma 3y2 plus 3y3 minus x1 minus x2. So simplification. Next, plus beta plus gamma RHS, that is equal to x1 y1 plus x2 y2 plus x3 y3. So for this we can write 3y1 plus 3y2 minus x1 minus x2 plus x3 comma y3. Now Again, this is of the form of x1 y1 plus x2 y2. So 3y1 and 3 into minus x1 minus x2 plus 3y3 comma minus x1 means minus 3y1 plus 3y2 minus x3. Simplification. Therefore, alpha plus of beta plus gamma is not equal to alpha plus beta plus gamma. Therefore, V does not satisfy the associative property. Therefore, V does not form a vector space.